Thanks, everyone. I will try to give a brief overview of electrolysis from Nell's perspective. I don't have to spend a lot of time on this based on the previous discussions, but certainly there's a conventional hydrogen industry and then certainly emerging areas in the power to X and mobility that we see as very fast growing and a big part of our business moving forward. Just a kind of snapshot on Nell itself. For those that don't know, we consider ourselves a pure play hydrogen company, unique in that aspect, providing kind of the entire production delivery value chain. We're located in basically we have 3 plant locations for each of the business or the product sectors that we're in. So I'm speaking to you from kind of the US operations where we're headquartered in Connecticut, where we manufacture the PEM electrolyzers, proton exchange membrane electrolyzers. We also have a plant in Norway where we do the alkaline electrolyzers. And then our sister group in Denmark does fueling station manufacture. So basically you can kind of see the experience and kind of capacity factors for each of these plants. Certainly, as we've announced, the big push now is in scaling up our manufacturing facility in Norway. And I'll talk a little bit more about that as we kind of go through the slides. But basically, we have a strong technology background and experience. We have a strong commercial experience and then manufacturing capacity to hopefully meet the demands of these new industries moving forward. Just a little bit of context in terms of talking about the PEM and alkaline. If you look at kind of historically, the alkaline electrolysis technology has, over 100 years or nearly 100 years of history in industrial applications, really kind of designed and built for scale from the outset. Has advantages in terms of its operating efficiency and certainly also from a CapEx perspective. It has some limitations in terms of its current densities due to kind of transport issues with gas generation that we can talk about. Conversely, the PEM systems were really developed to support kind of life support applications where oxygen was the valuable product in aerospace and military applications. And so high reliability, relatively small scale as compared to the alkaline systems, and certainly high cost. And so as you see the kind of commercialization history of those, they've kind of started from small scale and have been developing to larger scales, kind of moving forward in contrast to the alkaline system. There's just some details on kind of the cell designs and, kind of comparative differences about how things are kind of put together. I won't spend a lot of time on this. Hopefully, I think, just suffice to say, the significant differences in terms of materials of construction, typically precious metals on the PEM side versus non-precious metals can be used on the alkaline side, which gives it a cost advantage. But certainly from a footprint size perspective, the alkaline systems are quite a bit larger comparatively than the PEM systems, tend to be more compact. And then the solid state electrolyte and high bubble point of the memory material typically lends itself to high gas purity and also some operability advantages in terms of response times and start-stop behavior that differentiate the two technologies. And then if you look at kind of scaling, so, this certainly one way to reduce cost is to scale in terms of the product design. So again, you can the top line kind of shows some historical perspective from the alkaline side, where the building block today starts at about a 2.5 megawatt stack with associated balance of plant. And then we've been progressing the design to try to do shared balance of plant with larger stack sizes or multiples of stacks. And so some configurations that we have ongoing in terms of scaling to 5 and 20 megawatt, and then using that 20 megawatt module then in further scaling up design to address hundreds of megawatt plant sizes. And so that's how we see the progression from the alkaline systems to address the larger market needs as we see these market applications emerging. Whereas I said before, if you look historically from the PEM side, we have a lot of history in selling small products, appliances, if you will, in cabinets, in great contrast to how the designs on the alkaline side have been in the past. But we're essentially transitioning that approach as well. So today, the largest unit that we have is a 2.5 megawatt packaged containerized system based on a 1.25 megawatt stack. And we see that progressing now towards more, again, akin to what we see on the alkaline side, shared balance of plant with multiple stacks in more type of indoor purpose-built building arrangement that can then be scaled up further as well. So they are converging from a design perspective, and what you're doing is you're leveraging the cost of that balance of plant across a wider number of stacks in order to drive that cost down. And then certainly you have some economies of scale in making a higher volume number of repeat components. When you look at it from a technology perspective, so not just simply scaling the product size up, but how they compare. So this is a somewhat standard chart looking at cell efficiency as a function of current density, or you can think of it as hydrogen production per a fixed, say, electrolyzer area size, if you want to look at it that way. And then instead of current cell efficiency, you can think of it as the amount of production for a fixed amount of energy on the y-axis. Typically, at all cases on the current density, the PEM systems typically have a higher efficiency than the alkaline systems, but a higher capex. So when you look at where you'd like to operate at high efficiency at the low current density, the PEM systems traditionally have been at higher capex versus the alkaline systems. And then conversely, you have, due to the limitations of the technology, you haven't been able to drive the alkaline systems out to higher current densities, which would be a pathway to further reduce the capex portion. So, so I think as we look at this, we think certainly the PEM has potential for a lower capex by being able to drive the efficiency up at a given operating point. And we see, as I'll talk about, some substantial, ability to reduce that capex through technology development. On the alkaline side, it's really more I would say, incremental improvement on the technology side, although we do have a robust technology roadmap to do that in order to kind of progress the current density operating point higher for the alkaline systems to decrease CapEx. But again, a lot of the alkaline now is focused on just higher volume manufacturing capability in order to also drive down that cost. And then lastly, from the PEM strategy, certainly a key aspect of the PEM electrolysis is to leverage the knowledge base and the developing supply chain and partners from the fuel cell side, and capitalize on that, something that you don't necessarily get on the alkaline side. This is just kind of another way to look at this CapEx. OpEx is kind of breaking it down. I think there was some kind of discussion of this already, but the way we look at it, kind of, if you look at the pie chart of the system cost breakdown, you see it's substantially weighted on the cell stack, not surprisingly, but also power conversion takes up a big piece of that. If you take those two pieces together, you're talking, a vast majority of the overall cost of the system. So that's where we focus a lot of our efforts in terms of technology development and cost reduction. What we see is, if you look at the kind of the balance of plant components, they really kind of scale with kind of this, kind of the general engineering rule of 6/10 in order to basically, we see that as how that's being reduced with increasing scale, and that goes back to what we were talking about in terms of shared balance of plant over a larger number of cell stacks. On the cell stack side, we do have various technology improvements through various methods that we'll talk about to kind of reduce that cell stack cost. And then from an efficiency standpoint, really the two big items are the oxygen electrode overpotential efficiency losses there, and efficiency due to the membrane. So in that case, really, we're looking at advanced materials and higher operating temperatures to kind of address both of those elements from a technology development perspective. So as I said, we see certainly with scale up, with some advanced stack development from the advanced materials that we've talked about, being able to increase current density in order to kind of drive more hydrogen production from a fixed CapEx size. And then lastly, the integration with lower cost power electronics, matching up that power electronics with kind of the current voltage stack profile to optimize that, is a way we think can substantially reduce the current cost of, this is the PEM electrolyzer in this case. So we certainly see achievements of I'll say in the next 5 to 6 years or so, maybe reductions down to below $400 a kilowatt, really just through technology improvements, and then further reductions due to manufacturing scale and automation. And this just shows an example of the ability to actually do some significant cost reduction. So this is some work that we had done looking at basically the bipolar plate of the electrolyzer, and through some fundamental R&D, some prototyping, some accelerated testing, we've been able to show a 80% cost reduction for this component within the PEM electrolysis stack, and then taking that to scaled up to our current size platform for commercialization. and we see, opportunities like this moving forward, certainly with various elements within the current stack, and also, again, the ability to address that from a manufacturing perspective also. And then this is to talk a little bit about the alkaline technology. So this is our current plant expansion in Norway, and we're going basically from about 40, 50 megawatts per year of production to up to 500 megawatts per year, and then by adding additional lines, we room to expand to up to 2 gigawatts per year at this site. So very exciting, and something where we're betting on the market in advance. We're making the investments in order to be able to drive our costs down to get to a competitive situation, so that we can open up some of these early markets, and then hopefully that will drive additional volume, which drives additional cost reduction. So I think it's something that Nel as a company is kind of somewhat unique in committing these funds ahead of the market in order to do this. But again, that's part of our strategic plan, and then we have similar expansion capacity plans on the PEM side as well as we move forward. So just kind of maybe a last summary in terms of where we see kind of the activities needed. So we certainly believe there's significant stack reduction cost reduction that's achievable on the PEM side through advanced materials and process development, and leveraging the fuel cell community. And I think it's really more engineering activities on the balance of plant side in order to take advantage of that from current industrial process design practices. On the alkaline, it's more incremental on the cell stack design to improve current density, and really a lot of the current investments are in manufacturing volume scale up, including automation and advanced manufacturing processes there. As I mentioned, a key area is the kind of optimization of the stack versus the rectifier in order to get to a lower cost power conversion. And then also looking at the best way to interface with these variable renewable sources as we move forward to take advantage of that low cost electricity. Certainly the supply chain is underdeveloped for where we see the market going. So that's a key area, again, where I think we see ability to reduce cost as we work with our supply chain partners in order to get a compound effect in reducing the cost of those components. And just to comment, to date, there's things are really driven by small companies if you look at it compared to other industries. And so we feel like there's certainly ability as larger companies come into this space to add their expertise and their balance sheets. It's a way to drive that down further. Just as a frame of reference, I think we're up to maybe global electrolysis production is somewhere in the 250 megawatts per year capacity range. And as I think Mark had pointed out, I mean, I look at one ammonia plant that's being talked about in Western Australia that's to replace 50% of their natural gas production. For that plant, they need somewhere on the order of 1.5 gigawatts of electrolysis. So, 10 times the amount of current annual production of electrolysis. So certainly in one plant, in one location, in one market. So there's certainly a lot of work that we have to do to get our scale up, but also I think it just goes to speaks to the opportunity there to also reduce costs with volumes of market that we haven't seen before. That's all I have. I have a couple of slides at the end that I'll provide just some of the projects that we're working on. This is a project we recently announced with Iberdrola for ammonia production, for fertilizer production in Spain. We have working with Statkraft for steel production in Norway. Another steel pilot plant with Hybrid in Sweden. And so there are certainly examples kind of coming on board in terms of some of these pilots to prove out the technology. I think that is key for us kind of moving forward is these pilots in these emerging markets in order to really understand what the product requirements are, both from a operation and technology perspective, but obviously then from a cost perspective.